Look into my eye. Hello, it's Monaco here. I'm not sure why the webcam only records in the browser, but we're going to do lesson 5 for kinetics and equilibrium. So we're focusing on enthalpy and reference table I. Okay, this is our target. We want to be able to interpret those reactions for increases and decreases in potential energy based upon their delta H. So to read the heats of reactions on reference table I, you have to understand that the delta H for the reaction is the sum of all the energy absorbed to break the reactant's chemical bonds to form the activated complex at the top of our potential energy diagrams, as well as the energy released when forming the new chemical bonds of the product. So the overall delta H of the reaction is how much energy is absorbed or released in breaking all the atoms' bonds in the reactants, and then forming all the atoms' bonds in the products. The overall net change in heat is delta H. And so delta H is typically determined as heat of the products minus the heat of the reactants. The magnitude, meaning the sign of delta H, tells us how much energy is involved. The sign of that delta H means that it's either being released or absorbed. Okay? So changing the number of moles of reactants and products has an effect on the heat of a reaction. For example, if a reaction is written a certain way and we double the amounts, you're going to double the amount of heat that is involved as well. Think about it like this. If you burn one birthday candle, it's going to burn and release a bunch of heat. If you burn 2 birthday candles, they're both going to burn and release double the heat. So if you double the ingredients, you're going to double the amount of heat involved in the overall reaction. Now, if you half the amount of ingredients, you're going to half the amount of heat involved in the reaction. So it's like if I have a whole birthday candle that I burn, it releases X amount of heat. But if I cut that birthday candle in half and then burn it, it's going to release 1/2 X of the heat because there's only half of the candle. So if you half a reaction, you half the amount of heat. Now, you reverse a reaction too. Now, you can't unburn a candle, but many chemical reactions can be run in reverse. So you're going to reverse the amount of energy involved. The amount number-wise is going to stay the same, but you're going to reverse the direction the energy is flowing. So if a reaction originally releases heat, but you can run it reverse, it's going to absorb heat. So the magnitude of the delta H sign isn't going to change, but the sign is the negative heat values become positive, and positive heat values become negative. So exothermic in reverse is endothermic. And positive heat values become negative because endothermic in reverse, is exothermic. So that's how table I is kind of working. For example, I'm going to look on table I and I'll write these on the board. Got my table I here. There we go. Heats a reaction at 101.3 kPa and 298 Kelvin. Pick up a pen and I find the reaction N2 plus 2O2 makes 2NO2 on my chart. N2 plus O2 makes 2NO2 on my chart. There it is, about 10, 12 down. The delta H is plus 66.4, which tells me that that reaction is endothermic. And if I had to sketch a potential energy diagram, it would look like this, low to high. I drew it in blue because endothermic things feel cold. The next one, N2 plus 3H2. Let's find it here. Got to look through lots of N2 plus 3H2 makes 2NH3. There it is. The delta H is negative 91.8. Well, that's exothermic. More heat is produced than was absorbed. So it would feel hot. And I draw my potential energy diagram like that, the reverse of the roller coaster that I had before. The last one, 2NH3 makes N2 plus 3H2, is the same reaction, but flipped. Say we took the 2NH3 and drew it on the left-hand side and the other ones and drew them on the right-hand side. So we flipped the reaction, which means that we got to flip the sign of the delta H, which makes it not exothermic anymore, but endothermic, and switches the direction of heat's flow, which changes the sign of the heat flow, but not the magnitude of the heat flow. And that's how you read table I to find heats of reactions. You read the heat, you determine if it's endothermic or exothermic. Maybe you have to look and see if the reaction's been flipped backwards to front, or maybe it's been doubled. But that's what we do. Okay, so I'll see you in lesson 6. Adios. Adios.